Okay, so next, let's welcome Qingyao Tian, the speaker from the fourth oral talk titled EndoMamba and Efficient Foundation Models for Endoscopic Videos with Hierarchical Pre-training. Welcome.
Hi, everyone. My name is Tian Qingyao, and I'm glad to present the work EndoMamba, an efficient foundation model for endoscopic video analysis. In minimally invasive surgery, video-based tasks like navigation and surgical face recognition are critical as they give surgeons real-time support, helping them make quick, accurate decisions. The core challenge in endoscopic video analysis is to efficiently capture and estimating spatial temporal information. Most prior research has tackled this by designing task-specific models, for example, models tailored to surgical face recognition or navigation. While effective for a single task, these approaches often lack generalization and struggle when applied to new datasets or unseen clinical scenarios, and this limits their practical use in real-world clinical settings. In contrast, foundation models have shown remarkable success in general video understanding. They serve as a backbone across diverse downstream applications. And motivated by these advances, our goal in this work is to develop a video foundation model tailored for endoscopic tasks, one that combines strong generalization with the efficiency required for real-time clinical deployment. To build a foundation model for endoscopic video, one of the key obstacles is the computational inefficiency. Most existing backbones require recomputing information from past frames. For example, in the model shown on this slide, if we want to recognize the surgical face of the current frame, we require to repeatedly processing all previous frames. And if the backbone is transformer-based, which is the dominant approach, the complexity grows quadratically with sequence lengths, and this leads to high memory usage and slow inference speeds. But in surgery, where surgeons depend on real-time video feedback, delays are unacceptable. The second challenge is data scarcity. Unlike natural video datasets, which are massive and richly annotated, endoscopic datasets are relatively small and often lack paired vision language annotations. And this makes it difficult to directly apply large-scale pre-training strategies such as contrasted learning. To overcome this, we need a data-efficient pre-training strategy that can learn strong, generalizable video representations, even under limited supervision. To address these challenges, we propose EndoMamba, which has two key innovations: a computationally efficient backbone based on state space models, and a data-efficient hierarchical pre-training strategy. Before introducing our proposed model, we first outline deep state space models, which is the foundation of EndoMamba. SSMs efficiently handle long sequences by evolving a hidden state, H, over time, updating it with inputs, X, and generating outputs, Y. Mamba extends this framework with adaptively state updates for long-term memory and recurrent inference for computational efficiency, while also supporting sequence-to-sequence estimation similar to transformers. Building on the concept of state space models, here we introduce the EndoMamba backbone. The design goal is clear. We want to retain strong spatial temporal modeling ability while ensuring the model is efficient enough for real-time surgical applications. To achieve this, EndoMamba combines two key components: bidirectional scanning within frames and causal scanning across time. We start by converting the input video into patches. To retain positional awareness, we add both spatial and temporal positional embeddings so the model understands where each patch belongs in space and time. To effectively capture spatial representation within each frame, EndoMamba performs bidirectional scanning across image patches. This allows the model to aggregate information from all directions, similar to having forced spatial attention, but in a more efficient way. While the diagram shows bi-member blocks applied to each frame separately, in practice, we simply rearrange patches and process them in one forward pass, making the computation more efficient. After spatial modeling, the tokens are rearranged back to their frame-wise structure. These are then passed into member blocks that perform causal temporal scanning across frames. This step captures the temporal evolution of surgical scenes. Finally, the processed tokens are fed into an MLP head to produce the prediction. An important strength of EndoMamba is that it works efficiently in both training and inference. During training, we can process entire video clips in parallel, which speeds up learning, as shown in Figure B. But during inference, the model can switch to sequential processing, which makes it more efficient when handling continuous video streams, as shown in Figure C. Another biggest challenge is the lack of large paired vision language datasets and the fact that existing medical video datasets are relatively small. To overcome this, EndoMamba uses a hierarchical pre-training strategy. First, we apply unsupervised pre-training through low-level video reconstruction, so the model learns to capture spatial temporal patterns. Second, we introduce high-level feature alignment by distilling knowledge from a stronger teacher model. This combination helps the backbone generalize beyond the limited medical data. The first part is the low-level video reconstruction. Here we mask large portions of the video input and train EndoMamba to reconstruct them. This forces the model to exploit correlations across both space and time. By predicting the missing pixels, EndoMamba learns contextual dependencies and builds strong spatial temporal representation, which is essential for medical video understanding. To further strengthen generalization, we introduce feature alignment with a teacher model. The idea is to align EndoMamba's internal representations with high-level features from a pre-trained video foundation model. In practice, this means that for masked regions, EndoMamba not only reconstructs the raw pixels, but also matches the semantic features of the teacher. This allows EndoMamba to benefit from knowledge learned on large-scale natural video datasets. Both objectives are then combined in the pre-training loss. As a result, the model learns fine-grained spatial temporal detail from reconstruction and semantic abstraction from teacher guidance. Now let's look at the results. On POM classification and segmentation, EndoMamba outperforms strong baselines, including foundation models in endoscopic domain and in general domain. For surgical face recognition, our method again delivers the best performance comparing to these foundation models and even achieves comparable results with some of the state-of-the-art in the task-specific methods. And importantly, in terms of efficiency, EndoMamba achieves stable frame rates across different temporal lengths, maintaining over 46 frames per second, even at long sequences, which makes it highly suitable for real-time surgical applications. Finally, I'd like to share how we apply EndoMamba in a real clinical project for bronchoscopy navigation. We fine-tuned the model to detect lumen anatomy in bronchoscopy views. EndoMamba achieves the highest accuracy and F1 score among all methods. And importantly, it shows a much lower variance in video-level accuracy, which highlights its strong generalization ability across different patient cases, and is a key advantage of using a foundation model for endoscopic tasks. We use anatomy detection and branch-level localization as a core module in our bronchoscopy navigation system. For full details, you can search for our PANS V2 paper. But here we show the overall navigation results. Starting from the input video and the reconstructed airway, we estimate the bronchoscope 6 degrees of freedom pose and render the corresponding camera view in virtual bronchoscopy. And you can see that the virtual view aligns very well with the real camera view, and the ground truth camera pose and the estimated camera pose match very closely. And in summary, EndoMamba brings efficient and reliable video understanding to endoscopic tasks, enabling real-time performance and strong generalization in clinical practice. And thank you for your attention. If you have any questions, I'm glad to answer it here and at the poster session at the morning of Friday. Yeah, thank you.
Thank you very much.
Okay, thank you.